Welcome back to our ongoing deep dive into the OEIS. Today, we're tackling sequence A00000, minimal triangle graph.
Minimal triangle graphs, yeah. It sounds a bit intimidating at first, but trust me, it's a fascinating sequence with connections to network theory and even beyond.
Absolutely. And for our listeners who maybe aren't as familiar with graph theory, could you give us a quick, explanation of what a minimal triangle graph actually is?
Sure. So imagine you have a set of points. We call these vertices in graph theory, and they're connected by lines, which we call edges. Now, picture a graph where every single set of 3 vertices forms a triangle. So that's where the triangle part comes in. The minimal part comes in when you realize that if you remove even one triangle, the whole graph breaks apart. It's like a delicate structure where every single piece is absolutely essential.
Yeah, I see. So it's like a network where every connection is crucial to maintain that.
Yeah.
Integrity of the overall structure.
Precisely. And this OEIS sequence, O000000, this tells us how many of these unique minimal triangle graphs exist for a given number of vertices. The sequence starts 1, 1, 2, 4, 9, 19, and it keeps going, and it grows surprisingly quickly.
That's interesting. Why does the number of possible graphs increase so rapidly as we add more points?
Well, as you add more vertices, the potential connections between them multiply. It creates this combinatorial explosion of possibilities.
Right.
And this just highlights the inherent complexity that emerges as networks grow.
I'm starting to see how this could have. Pretty significant implications for understanding real-world networks.
Absolutely. Think about social networks, transportation networks, or even biological systems. Minimal triangle graphs, they can provide a really useful framework for analyzing these complex systems and for understanding their vulnerabilities and points of failure.
That's a great point. Let's dive a little bit into the history of this sequence. The OEI's entry mentions that it was first studied back in 1967 by R. Bowen.
Yes, Bowen's work, the generation of minimal triangle graphs. This paper really laid the foundation for our understanding of these structures. It's amazing to see how this sequence has continued to intrigue mathematicians for decades.
We even have a research paper from 2014, published in Discrete Mathematics, that delves deeper into a related concept. 3 minimal triangle-free graphs. What makes these graphs so intriguing?
Well, triangle-free graphs, as the name suggests, contain no triangles. What's particularly fascinating about 3 minimal triangle-free graphs is their inherent stability. You need to remove at least 3 vertices to break them down into smaller graphs. They contain a key building block known as a P4, which is simply a path with 4 vertices connected in a straight line.
So every 3 minimal triangle-free graph has this P4 structure embedded within it. Why is the P4 so important in this context?
The P4 structure is fascinating because it acts as a fundamental building block for larger, more complex triangle-free graphs. Imagine it as a foundational unit that you can replicate and connect to create these intricate networks without ever forming a triangle.
That's a great analogy. It's like having a set of special Lego bricks that only fit together in certain ways, preventing any triangular formation.
Exactly. And the 2014 paper we mentioned goes even further. It provides a precise formula to calculate the exact number of these 3 minimal triangle-free graphs with a given number of vertices.
Oh.
This formula really unveils a hidden order within these seemingly complex structures.
I'm curious about the real-world applications of this. Where do we see these minimal triangle graphs and triangle-free graphs in action?
They pop up everywhere. Consider a social network. A minimal triangle graph could represent a group of friends where everyone knows each other, and removing one person would break the tight-knit circle. On the other hand, a triangle-free graph could model a communication network where you want to avoid information loops or redundant connections.
That makes sense. So understanding these graph structures can help us optimize networks for different purposes, whether it's maximizing social cohesion or ensuring efficient information flow.
Precisely. In transportation networks, understanding minimal triangle graphs can help identify critical junctions. Disrupting one of these junctions could significantly impact the flow of traffic. Similarly, in computer networks, knowing where the P4 structures lie can help identify potential vulnerabilities. Attacking those points could disrupt the entire network.
This is really highlighting the power of abstract mathematical concepts to have tangible impacts on real-world systems. It's fascinating how a seemingly simple idea, like connecting points with lines, can lead to such profound insights.
Absolutely. And the beauty of the OEIS is that it provides this vast repository of sequences, each with its own story to tell and connections to explore. Sequence A0000080 is just one example of how these seemingly abstract mathematical objects can provide a lens through which we can better understand the world around us.
So what does this all mean for our listeners? Why should someone who's not a mathematician care about minimal triangle graphs or the OEIS in general?
It boils down to this. Whether you're designing a social media platform, optimizing a transportation network, or even studying biological ecosystems, understanding the principles of graph theory as exemplified by minimal triangle graphs can provide valuable insights. The OEIS and its collection of sequences, including A00000, serve as a powerful toolkit for anyone seeking to uncover the hidden patterns and structures that govern our world.
This has been a fascinating exploration. We've journeyed from the abstract realm of minimal triangle graphs to their real-world applications and networks spanning social connections, transportation, and even computer systems.
What's particularly exciting is that we've only scratched the surface. There's so much more to discover about the properties of these graphs and their implications for diverse fields. And the OEIS, with its ever-growing database of sequences, continues to be a treasure trove of mathematical insights waiting to be unearthed.
Thank you for guiding us through this deep dive into the fascinating world of minimal triangle graphs and the OEIS. It's clear that even in the seemingly abstract realm of mathematics, there's a profound connection to the world we experience every day.
It's been my pleasure. And for our listeners, remember, the next time you encounter a complex system or network, take a moment to consider the underlying graph structures. You might be surprised by the insights you uncover.
Yeah, it's amazing how this deep dive into minimal triangle graphs has, unveiled this hidden order within these seemingly complex systems.
Yeah, and what's particularly intriguing is the elegance of that formula from the 2014 paper.
Right. To be able to quantify the number of 3 minimal triangle-free graphs with such precision, it's really a testament to the power of these mathematical tools.
It is. It allows us to move beyond qualitative observations.
Right.
And make precise predictions about the behavior of networks.
I'm curious about, the broader implications of this research for our listeners. What are some of the key takeaways they can apply to their own understanding of the world?
Well, one key takeaway is the importance of understanding connections, whether it's the connections between people in a social network, the connections between components in a machine, or even the connections between ideas in a scientific theory. Recognizing the underlying structure of these connections can reveal valuable insights.
It's like having a new lens through which to view the world, one that highlights the interconnectedness of everything.
Precisely. Another key takeaway is the power of abstraction. By abstracting away the specific details of a system and focusing on the underlying graph structure, we can gain a deeper understanding of its fundamental properties.
This reminds me of how a map can represent a complex landscape in a simplified way, allowing us to navigate more effectively.
That's a great analogy. And finally, I think the OEIS itself serves as a powerful reminder that there's a vast universe of mathematical knowledge out there just waiting to be explored.
Each sequence in the OEIS is like a hidden treasure, offering insights into unexpected patterns and connections. It's really a testament to the beauty and power of mathematics to illuminate the world around us.
It is. So for listeners, I encourage you to embrace curiosity, explore the OEIS, and see what mathematical treasures you can uncover. You might be surprised by the insights you gain and the connections you make.
Well, thank you so much for joining us on this deep dive into the fascinating world of minimal triangle graphs and the OEIS. We hope you've enjoyed exploring these concepts with us. Until next time, keep exploring and keep asking those intriguing questions.